Hello, everyone. Thank you for being here. Today, I'm going to talk about how ultra-high order spatial independent component analysis, or ICA, can be used to identify fine overlapping functional parcellation and also capture a spatial temporal reconfiguration. Previously, we showed that brain functional organization spatially evolved over the time, and this reorganization and reconfiguration include variation within brain region and also variation and changes in spatial topography of functional organization. In other words, we are saying our findings suggest that in addition to variation in temporal coupling, that commonly known as dynamic functional connectivity, a spatial pattern of functional organization also evolved over the time and change. To explain this concept, here I'm showing a toy example of 3 different dynamic behavior for a simple system with 2 latent sources. Each latent source has a spatial pattern and also a temporal pattern or activity. A system is temporally dynamic if the properties of temporal activity of the sources, which commonly measured through temporal coupling or covariance, varies over the time. A spatial dynamic system is a system that the spatial pattern of brain sources varies over the time, and if a system has both a spatial dynamic and temporal dynamic properties, we consider them as a spatial temporal dynamic. Oops. How can I go back? Okay. So while our previous finding highlight the necessity of explicitly incorporating space in dynamic analysis, it further emphasized on the importance of within subject variation and dynamic functional parcellation in addition to between subject spatial variation in functional analysis. And ignoring these variations could potentially result to inaccurate or even incorrect findings. For example, let's assume a system has 2 sources in red and green, and they have the same temporal coupling or connectivity, functional connectivity, over at 2 time points. But one of them, which is in green, changes over the space. So if we ignore this spatial variation and we assume a spatial fixed node for our analysis, we may incorrectly conclude that there is changes in functional connectivity. This is an ongoing project, so we have 2 aims for this project. The first aim is to generate a dynamic functional atlas or dynamic functional parcellation, and the second one is to use this parcellation to capture a spatial temporal configuration of brain functional organization through brain functional hierarchy. To achieve this goal, the first step was to leverage a multivariate ICA framework and adopt it to parcel the brain into functional units. A functional unit defined as a pattern of brain region with very similar functional activity over the time, of course, considering given the associated imaging modality. So in our case, it's a Bose signal. We have 300 subjects, but we can use it for other modality, and of course, better or higher data quality and resolution can improve the estimation of functional unit. For this project, we use ICA with 1,000 components, or 1K ICA, and we observe a fine granular overlapping functional unit. The figure in A shows the location of primary functional unit on the cortex. Basically, each voxel assigned to a functional unit or component that has a maximum strength or contribution. It is similar to what we do usually using regular hard parcellation using univariate approaches. And figure B showing the level of the multifunctionality or contribution of the voxel to other functional unit in addition to the primary functional unit. So we are trying to, this figure showing how much other functional unit in addition to primary one contribute to that voxel. It is kind of similar to what we do with partial correlation. We remove the influence of the first one and see the others. And results show loosely that in frontal and temporal area, we have a higher level of multifunctionality compared to, for example, to primary motor cortex. Next, we evaluate the temporal dynamic configuration of the pattern of functional unit using their similarity with the time course of large-scale brain network. We achieve that by using a regularized cost function that protects against spurious fluctuation, because we don't want any changes cause change in assignment. So at each window, we assign a functional unit to one of the network based on the similarity in their time courses. Our result shows that even for the spatially adjacent functional unit, we observe different temporal configuration. Here, for example, I'm showing three independent components or functional units that are in the posterior cingulate area, and they have a fairly good overlap, but their temporal profile changes over the time, and they are not the same. Interestingly, we observed that dynamic reconfiguration or within subject variation and between subject variation show a very similar pattern across the brain network. Of course, between subject spatial variation is higher than within, but interestingly, we see a similar pattern. The network that has a higher between subject variation also show a higher dynamic variation. To conclude, a considerable level of multifunctionality, particularly in temporal region, suggests the need of overlapping functional parcellation probably, and we are suggesting 1K ICA is a promising approach to produce a fine overlapping functional parcellation. And the other hand, dynamic reconfiguration highlight the importance of within subject variability, which was supported with high agreement between within subject variation and between subject variation. Overall, we are suggesting that considering the importance of both between and within spatial variation, there is a need to use a multivariate approach like ultra or high order ICA framework or any approach that are suitable to capture and get a personalized, fine overlapping dynamic parcellation. Thank you, and please come and talk more with me if possible at the poster this evening. Thank you.